Okay, good morning, everybody. So yesterday we talked a little bit about partition trees, some of the basics. So what I want to do today is, well, after a quick review of what I covered yesterday, talk about multi-level structures. So that's partition trees. I guess for those of you who know range trees, where you have, the first level tree is a binary search tree, and then each node has an associated structure. That's going to be exactly the same here, but now with partition trees. But first, let's quickly go over what we did yesterday. So, we looked at half-plane range queries. So you're given a set of points. You want to, let's say, count all the points below a line, so all the points in a half plane. And then we looked at two different structures for this. One was a partition tree, uses linear space but has roughly square root of n query time. And one is a cutting tree where you have much better query time, log n, but the storage is much higher. It's n squared or n to the 2 plus epsilon. And so let me very quickly go over it because we will need that later on. So the basic tool that we were using was what is called the simplicial partition. Right? So I have my set of points and endpoints, and you get a parameter r. And now you can compute a number of subsets, each with a triangle containing the subset. And the property is that out of those R triangles, if you have any line, it intersects only square root of R of these triangles. Okay, and then the structure was, for every, you take the root node, you compute such a simplicial partition for your point set, and then every triangle corresponds to a subtree, and, with that subtree, with the root of the subtree, you store the corresponding triangle, and in the subtree you recursively construct a structure for the points inside that triangle. Okay, and the query is simply, recursive. When you get to a node, if it's a leaf, you simply check if the point is inside your query. Otherwise, you look at all the children. If the triangle is fully contained in your range, it's fully contained in the half plane, then you report or you count the set of points. And so let me introduce a little bit new terminology. So the point set corresponding to a node, right? And remember, a node corresponds to a triangle. Okay, so that has a set of points, and this point set is often called the canonical subset of that node. Okay, so if the canonical subset is completely contained in your range, then you can simply add the number of points to your counter, and otherwise, if it has non-empty intersection, you go into recursion. And the third case is when the triangle is completely outside the range, and then you can ignore that subtree. Okay? So it's good to think about this in the following way. So what the algorithm is doing, essentially, it's going to select a number of nodes. So in the query algorithm here, I wrote report all the points or count all the points. But essentially one way to think about it is to say, okay, now I have a subset of my points. Okay, that's this canonical subset, of which I know that the subset, all the points are completely inside my range. Okay, so if I want to report them, I can just report all of them. If I want to count them, I just have to add the number of points to my counter, and so on. So the algorithm, the query algorithm, is going to find a number of nodes. Okay. such that the canonical subsets of these nodes, the union of them, contains exactly the points inside my range. Okay, so if I go back up here, so for instance, here I would select, in this example, I would select this node Wi. Okay, and then here and here, recursively, you're going to select some more nodes. Right, and if you look at these nodes, this collection of nodes, their associated subsets are exactly the points inside the range. Okay, so, and if you want to, like I said, report them, well, just report the subsets. If you want to count them, just add their numbers, their cardinalities. But what we'll do today is something where you want to do something more complicated. And then what you do is these canonical subsets, if you want to do something more complicated, you actually have to store it in another data structure to do this more complicated thing. Okay, so that's the basic idea, but, well, we'll spend the rest of this lecture more or less seeing how that works. Okay, and the number of canonical subsets, well, the query time was n to the 1/2 plus epsilon, so that's also the number of these nodes that you select. Okay, cutting trees, you can actually think about them in a similar way. So, well, the basic tool was a cutting. So, if you have any set of n lines, you can partition the plane into triangles such that any triangle is intersected by at most n divided by r of your lines. Okay, and you need r squared triangles to do this. And then the tree that we or the algorithm that we had was, well, again, it's a recursive algorithm. Say I want to find all the lines above a point. Okay, then I get to a node V with my query point Q. Well, if it's a leaf, simply check whether the line stored there is above your point. Otherwise, well, look at all my triangles in the cutting. Find the one that contains the query point. Okay, and then, well, with this triangle, I have this set of lines which are above the triangle. Okay, that's L plus of my triangle delta I. This is the canonical subset of that of the corresponding node. And, well, if you want to report, then you report all of them. If you want to count, then you simply add the cardinality to your counter. And, well, then after doing that, you have to recursively search in the subtree corresponding to that node. Okay, so again, you can think about this as, well, if you want to find the lines above a point, this structure allows you to select or find those lines in, well, in this case, a logarithmic number of subsets. Okay? So this is one of my subsets, and then when I go down in this tree, I get at the next level, again, I have a number of triangles. I mean, one of those triangles correspond to a node that will give me a second canonical subset, and so on. Okay, so essentially every time you get to this line 4, right, so in every call you will get here, and that gives you a node, and all these nodes together, their canonical subsets are going to be exactly the lines that you want. Okay, so here you could say, well, select this canonical subset, and now again, the set of points inside my half plane H is exactly the union of all these canonical subsets. So this is, what we did yesterday. Now looking at it in or talking about it maybe in a slightly different way. Now let's see what we can do with that. So the problem I'm going to look at as the first example is range searching with a triangle. Okay, so now the range is not simply a half plane, but it's going to be a triangle. Okay, so what I'm going to do is first see if we want to use a partition tree. Okay, so I have linear storage. How can we adapt it, or if we need to adapt it at all? And then go to cutting trees. So if we want to have logarithmic query time, how can we adapt it from half planes to triangles as queries? So if you think about the partition trees, it's actually nice because you don't have to change anything at all. Okay, I simply have my partition tree. I don't change anything. But now in the query, the only difference is that instead of searching with a half plane, I now have a query triangle. Let's call the triangle Q for query. And then you do the same thing. Right? You arrive at a node. If it's a leaf, well, check if the point is inside the triangle. Otherwise, look at all the children of your node. Okay. If the triangle of that child is fully contained in the triangle, well, then all the points are also fully contained. So you simply report or count or whatever you want to do. Otherwise, so in this example, there's one triangle which is completely contained in it. So that corresponds to this subtree. So I don't have to go into recursion. Because I know that all the points are inside. But for this subtree corresponding to this triangle, well, some points may be inside, some may be outside, so I go into recursion. Okay, so that's, in this case. Okay, so do I have to change anything in the analysis of the query time?
Maybe we have to check with 3 lines. We can cross all of the triangle. So we have to check all of the children of a root.
Okay, so indeed that's exactly what we have to think about. So the crucial element in the partition tree was that you don't have to recurse in all the children because a line intersected only square root of R of our triangle, of our triangles. And now the boundary of the range is not a line but is a triangle, so maybe we can intersect many more. Okay, so that's exactly what we have to worry about. But fortunately, if you think about it, not that much can happen. So this was the analysis we had before. Okay. What's the query time? Well, at the leaf it's constant. Otherwise, I'm going to look at all my triangles. Okay. And then for square root of R of them, I have to recurse. Okay? And I get this bound because I know that a line intersects only order square root of R. A line intersects only order square root of R of the triangles of my partition. So now if I have the boundary of a triangle, how many of the triangles in my partition can it intersect? How many of the triangles can be intersected by one edge of my query? Square root of R, right? I know that definitely the whole line through the edge intersects only square root of R of my triangle. So definitely this edge also. So that means that the number of things I can intersect is simply only 3 times what I had before. Right? Each of the edges could at most intersect order square root of r of my triangles. And, well, this was big O anyway, so I can just forget about the 3 essentially. So the analysis will be exactly the same. Okay, so the only thing that changes because of the 3 is that the constant in the bound eventually will, I guess also here, this will be multiplied by 3 or something. Okay, so if I want to do range searching with a triangle instead of a half plane, and I want to use partition trees, then it's easy. I don't have to do anything.
Excuse me. One of the changes here, I think we need a bigger R for this data structure, don't we?
Okay, so you're right in the sense that if you give me an epsilon, okay, I had to pick the value of r large enough to get this bound. So now probably I have to pick a slightly larger r maybe to get this bound. So in that sense, the value that I have to pick, this constant value is going to be a slightly larger constant to get to this bound. Yes. Okay, so now it's getting a little bit more interesting. So remember that for cutting trees, we had to go to dual space. Okay, so here, yesterday, if we wanted to find all the points below a line, then we said, okay, in dual space, now I'm given a set of lines. The query is a point, and I want to find all the lines above that point. Okay, and I use the cutting tree for this. So now, if I want to find all the points in a triangle, okay, what does it mean? Well, this point is above this line, below this line, and below this line. So here, I can look at the dual point of this line. That's maybe here. The dual point of this line is here, and the dual point of this line is here. So all the points that are here, well, they have to be let's say above this line. So this point, they have to be below this point. They have to be below this line, so here above this point and above this point. Okay, so the lines that I'm interested in are the lines that intersect each of these 3 half lines. Okay, so the query would be something like, given you have a set of lines, given 3 points, 1, 2, 3, find all the lines that are, say, above point 1, below point 2, and above point 3. Okay? And whether it's above or below depends a little bit on the triangle you have. So in here, I have it's above one line and below 2 others. Of course, my query triangle could also look like this. And then I want to find the points above this one, and below this one. So then I would have 2 things going down and 1 going up. Okay, but that's that doesn't really matter. So let's just for now think about this example where I have 2 things going up and 1 going down. Okay, so we know how to look at this problem in dual space. Now let's see if we can use a cutting tree. Okay, so I have, well, my cutting. For every triangle, I have a child of the roots, a subtree. And now how do I do the query? Well, that's because you can somehow think, well, I have 3 points, so maybe I have to go down in 3 subtrees or something. But if you think about it, that's not going to work, right? Because if I go down here, let's say, because for this point, then if I forget about the other points in here, then that doesn't work. So I have to do something else. And so the key idea is, remember that for a cutting tree, also for a partition tree, we could, if you query with 1 point, okay, you essentially get all the lines, say, above that point in the form of a logarithmic number of these canonical subsets. Okay, so stated differently, you can select a logarithmic number of nodes such that the canonical subsets of these nodes contain exactly those lines that are above your query point. Okay, so if you think, but now what we want, well, let's for now start with having only 2 points. Okay, so I want to find the lines above here and below here. Forget about this for a moment. If I now do my normal search with this point, okay, going down the tree, I select log n nodes, and I know that all the lines in those canonical subsets, they already satisfy the condition that the lines are above this point. Okay? But I also want that they are below this point. So what I do is, as soon as I have, let's say, this is maybe one of the nodes I select, I know that its canonical subset is already above, all the lines are above this point. So now I want to do some more filtering, you could say. Okay, I already filtered out the ones that are above this one, but now I want to filter out the ones that are below this one, or select the ones that are below that one. So I have a second data structure which is going to store this set, and that I can use to check for this second condition. Okay, so this is what's happening. So here I have my canonical subset. Okay, I do the query with this point. I come here. Instead of reporting all those lines, well, I'm not allowed to report them yet, because some lines may be above the second point and some may be below. So what I do is, in my data structure, I'm going to store this set of lines in another data structure. So not just as a list or the number, but as another data structure, such that we can report all the lines below another query point. Okay? So what data structure do I have to use for this? Another cutting tree. Okay, so of course, before I do the query, right, I can do lots of different queries. I don't know where my first point is going to go. So the data structure for all of the nodes in this first cutting tree, each of these nodes is going to have some second data structure, some associated structure, which stores the canonical subset of that node in the form of a cutting tree. Okay, so, well, now I have a two-level cutting tree. The first level was to deal with point Q1. The second level, and the second level is actually lots of trees, one for each node at the first level. Okay, this second level is going to be, well, another cutting tree storing this canonical subset. Okay, and then, so I have my cutting. For each triangle in the cutting, well, I have a second level tree, which is a cutting tree on the canonical subset. And then in here, I have a recursively defined two-level structure on the set of lines that go through this thing. Right? So also here, this node is going to have a number of children. For each of those children, again, I'm going to have all these second-level trees. Each of those children is going to be the root of a recursive structure. Those, again, are going to have lots of trees hanging from them, and so on. Okay, so it seems that we're going to use a lot of storage, but we'll see about that. But first, let's have a look maybe at the query algorithm. Okay, so I hope that if I would give you some time, you could actually maybe write the query algorithm for yourself. But let's see how it works. Okay, so my query algorithm, I call it report above point A and report above point and below second point. Okay, so it gets 2 points. I want to report all the lines above this point and below this point. Okay, and now let's see what happens when I arrive at a node in my tree. Okay, so I'm at well, let's say I start at the root there. Okay, when I'm at the leaf, well, simply check whether the line is above this point and below this one. Otherwise, well, find the triangle that contains the first point. Okay, so simply look at all the triangles, find the one which is containing my first query point. Okay, then I know that the canonical subset of this triangle, of this node, so all the red lines, I know that all of them are above Q1. Okay, so now I go to my second level structure, so let's say the red thing there, and I'm going to do a query just with my old query algorithm in that cutting tree with just a point Q2. Okay, so I'm going to report all the lines in the red set which are above Q2. And I have them stored in a cutting tree, so we know how to do that. Okay, then the only other lines that I have to worry about are the lines that are passing through this triangle. They could be, well, above Q1 or below Q1, and above Q2 or below Q2. So I have to deal with them, and that's simply a recursive call. Okay. So
Line for, shouldn't you report below point Q2, because Ti plus are the set of lines that are already...
Okay. So yes. Sorry, this should be below. Yeah. Thank you. Okay. What's the query time going to be? Okay. So if you just, well, I'm going to write the recurrence, but actually it's not really needed. So at the first the first level tree, how many nodes am I going to visit? Log n. For each of those nodes, how much time do I spend? Well, I do a query in another cutting tree. How much time does that take? Log n. So log squared n. Okay. We can also do it a little bit more complicated. This one? Ah, okay. We can also analyze it a little bit more complicated or formally with a recurrence. Okay, so what happens? Well, again, at a leave constant time. Otherwise, we're going to look at all the triangles, find the triangle containing our query point, then do one query in this second level tree. Well, we use our result from yesterday that a query in a cutting tree takes log n time. And I'm going to recurse in this subtree. Okay, and again, if you take just a constant r, this is going to solve to log squared n time. Okay, let's see how am I doing. Let's do that later. So actually, there's a nice trick to get rid of the square, but maybe I have some time for this later. So, how much storage do we have? Well, if you analyze this in a naive way, then it's going to be a lot of storage. How many nodes do we have in this first level cutting tree? What was the size of a cutting tree? Right, n squared, or n to the 2 plus epsilon. So I have n squared nodes. Each of them is going to have another cutting tree. So if you just say, okay, n squared nodes, each of them has a cutting tree which is also n squared, you will get n to the power 4. Okay. Fortunately, it's much, much better than that. And the reason is, if you think about all these cutting trees, so this is my first cutting tree. Okay, the root is going to have something here. These are going to have something. Oops. So all of these. So I have lots of these trees. Okay, but of course they are not all of size n, right? If I look at a node here, then well, this probably only has a few lines here, so also this one is going to be pretty small. So hopefully when you sum all these sizes in the correct way, hopefully it will be better than n to the power 4. Okay, so let's try to do that. So obviously I'm going to write a recurrence for the amount of storage. So here's my recurrence. Okay, so I have r squared triangles in my cutting. For each one of them, I'm going to have a cutting tree as a second level tree. So I know that this cutting tree, well, we used the bound from yesterday, that's n to the 2 plus, well, let me write some epsilon prime here. Okay, plus, well, for each one of these I'm going to recurse. Okay, and well, it's, again, if you think about it, and if you think about the master theorem, so I perhaps you remember that if you look at this term here, since I've r squared and here n divided by r, okay, you would hope that the solution is going to be n squared. Except because of the O here, I get n to the 2 plus epsilon maybe. And in the master theorem, well, it's either determined by essentially this recursive part, where if I have a square here and here r, you get n squared, or it's determined by the overhead, depending which one is better, which one is larger. And here this overhead is also roughly n squared. So actually it turns out that if you do the computations, you can get for any epsilon, well, then I have to pick this epsilon prime, maybe epsilon over 2. I have to pick a large value of r, and then you can get n to the 2 plus epsilon. Okay, so I'm not going to write or do the derivation here, but maybe let me just say something related where you also have something, well, a multi-level tree which is better than what you would expect. So if let's say, if you look at a range tree, okay, a two-dimensional range tree. Okay, so that's a binary search tree, okay, on x coordinate, and for every node, okay, I have a binary search tree on y coordinate. Okay, here you could also say, well, this binary search tree has n nodes. Each of the trees of the second level also has linear size, so I would get n squared. But what do I get here as storage? The storage for a two-dimensional range tree. Well, n log n. And one way to see that would be to say, okay, the root here, my second level range tree is really big, also size n. But the two children of the root, here I essentially have size n over 2. Here I also have n over 2. So together, this is also n. The next level, here I have n over 4. Here I have n over 4. N over 4. N over 4. So the next level is also n. Well, I have log n levels, so I get n log n. So basically, because the sizes of these second level trees decrease rapidly, if you sum up all the sizes, you don't get the blow up in storage is kind of under control. So here exactly the same thing happens, except that the formulas are a little bit more complicated. Okay. So I hope this is clear. But so now let's go back to the problem that we wanted to do originally, where we actually had 3 points. Okay? The 3 points corresponding to my triangle. So in primal space, I had a set of points. I come with a query triangle. Okay. In dual space, I have a set of lines. Each of the lines through the edge of my query becomes a point. And I want to report all the lines, say, above here, below here, and above here. Okay, so how do I do it? Okay, so one suggestion would be to say, do the query for Q1 and Q2. do the query for Q1 and Q3. That gives you 2 sets of answers, and then take the intersection. Okay, that works. But the query time is not going to be very good. And the problem is that it could be that you have lots and lots of lines that are good for Q1 and Q2. So you report all of them, and then later out you find out that they are not good for Q3. So it works, but it's not very efficient. So at another level, exactly. That's what we're going to do. So so what we did before, we said, okay, if I query with Q1, okay, here I have a cutting tree, and then what I needed to do before on this canonical subset, report all lines that are below Q2. Now what I want to do on this set is report all lines below Q2 and above Q3. So this structure should be able to do a query with 2 points, Q2 and Q3, and report all the lines above one of them and below the other. Well, we just saw how to do that, right? So this is now going to be a 2-level cutting tree. Together with this, we get a 3-level tree. And that's it. So this thing is going to be, another tree with lots of trees hanging from it, because it's a 2-level tree. And the query algorithm, I'm going the wrong direction. Oops. Okay. So now I would have something like report above 3 points, or above point 1, below another one, and then so on. Algorithm exactly the same, except here I get report above point and below second point. And here I have report above point, below second point, and above third point, or something. Okay, that's the only thing. Okay. So what's the query time going to be? Log to the power 3. Right? In the main tree, I select log n nodes. For each one of them, I do a query in this 2-level thing. So that takes log squared n. So together, log times log squared is log cubed. Okay? And again, if I want, I can write a recurrence. Right? The query time is, look at all the R-squared triangles. For one of them, you do a query in the associated structure, which is now a 2-level tree, and we just proved that the query time is log squared. And I have a recursive call. Okay, so what happens to the amount of storage? Well, if you think about it, nothing, or at least not asymptotically, because if we write the recurrence, so the only thing that I have to change is that here, okay, I have to write the amount of storage of a 2-level cutting tree, right? Because my associated structure, it used to be a 1-level cutting tree, but now it's a 2-level. But we just saw that for the 2-level, I can also get n to the 2 plus epsilon. So I get the same thing and nothing changes. Right? So of course, it cannot be that you have exactly the same amount of storage because you had the same thing and you have lots of other trees hanging from it. So what will happen is that the constant here is going to change. Okay? Okay, so here's high-level summary of what we did, and it helps to, if you understand what is going on, it helps to think about it in this way, because then for lots of other query problems you can easily see whether this solution applies or not, whether you can do something like this. Okay, so you have, well, here we wanted to have all the lines that satisfy three conditions. Okay, condition 1, they should be above point 1. Condition 2, they should be below another point. Condition 3, they should be, let's say, above a third point. Okay? Each of these conditions is going to give a level in my multi-level tree. Okay? The first level tree, or the main tree, is used to check or to select the data or the lines that satisfy the first condition. Okay, and in this case, our condition was that the line should be above Q1. Those I essentially get in the form of log n canonical subsets, or you can say log n nodes whose canonical subsets are exactly the lines that satisfy the first condition. For each of these canonical subsets, well, I also need to worry about the second condition. So for those canonical subsets in my data structure, I have a second level tree, which is going to help me find the ones that also satisfy the second condition. Okay? So for each of these canonical subsets, I have an associated structure, in this case, again, a cutting tree, where I can deal with the second condition. So the ones I can select the lines that, well, are below Q2. Okay, and because I only look at this structure for a canonical subset that was already above Q1, I now have both conditions. Okay. I have a third level where I check for the third condition. Okay. So essentially, a very high level view. If you have a query problem and you can express that query problem as, okay, the elements that I want to report or count or whatever are the elements that should satisfy condition 1 and condition 2 and condition 3 and condition 4. And each of these conditions is basically a half plane condition. Then you can have a multi-level cutting tree. You could also do, we'll see that in a moment, a multi-level partition tree in exactly the same way. Okay, so for triangle array searching, for a partition tree, you don't need this multi-level because you could do it directly. But in a different scenario, as we will see, you will also need that. So this is the theorem that you get. Again, it also works in higher dimensions, and then the storage simply goes up. And, well, this was just the summary for triangle array searching. We simply kept linear storage and to the 1/2 plus epsilon. And for all the things that I'm saying here, there's lots of well, small tricks or improvements that you can make. Like often you don't need these epsilons, and instead of the epsilon maybe you get polylog, or sometimes without the log, but that's essentially all technicalities. And I think nowadays when you write a paper and you need some multi-level partition trees, then people don't really care so much anymore about whether it's epsilon or polylog, because that's supposed to be, well, standard machinery. You just have to show essentially that you can use these things and plug it in, and then, well, what are the exact bounds is a little bit less interesting maybe. Okay, let me do another example to show how you can apply this. So suppose I give you a set of line segments, and the query is, given a line, report all the segments intersecting that line. Okay, and I want to have a structure that uses linear or maybe n log n or something like that storage. Okay, so how are we going to do this? Well, we're going to express this problem as, okay, I want my elements are now line segments. I want to find all line segments satisfying some condition. So the condition was line segments intersecting the query line. But I'm going to express that as two half-plane conditions. So how can we do that? Yeah, exactly. So if I have a segment, it intersects this line only if and only if one endpoint is below and the other endpoint is above. Okay, so those are two half-plane conditions. So I should be able to use a multi-level partition tree or cutting tree, whichever I want, whether I want to have log n query time or near linear space. Okay, so we need a two-level partition tree. Okay, high-level view. The first level is going to intersect, let's say, all the segments where the left endpoint is below the line. And then in the second level, I'm going to, out of those, select the ones that have the right endpoint above the line. Okay, and I should also do the opposite case. Okay, so, well, I'm going to build my first level. I want to find all the segments where the left endpoint is below the line. Where the left endpoint is above the line, I guess, in this picture. Okay, so I have a partition tree where I store the left endpoints. Okay, so all the left endpoints here, as you can see, they're in this partition tree. Okay, so what is the query going to do? Well, when you get to a leaf, that's easy. Otherwise, you look at all the children of the root. Okay, if the triangle lies completely below the line, if the triangle lies completely below the line, then all the left endpoints lie below the line. So from those, I want to have the ones where the right endpoint is above the line. So what do I do here? Well, for this canonical subset, I want to report the ones with the right endpoint above the line. And here, it's just the opposite. Right? If the triangle lies completely above the line, then here I want the right endpoints to be below the line. Otherwise the triangle is intersecting my query line, and then I have to do a recursive call. Okay. So how is my data structure? What is it going to look like? Okay. So here you see that for this associated structure, to test this, I have a partition tree on the right endpoints. Yeah. Is the idea clear? I hope. Good. So, what's the query time? Well, again, we can do sort of a naive argument. We could say, well, in the first level tree, how many nodes do we select? Well, for a partition tree, we selected something like square root of n nodes, or n to the 1/2 plus epsilon. For each one of them, I'm going to do a query in my second level structure. Okay, also taking n to the 1/2 plus epsilon. Okay, multiply, you get linear. Root n times root n, which is pretty useless. Right, so hopefully we have the same situation as before when we were looking at the storage for cutting trees, namely that the fact that not all of these second level trees are big, many of them are quite small, so we're not always multiplying by square root of n, but we're multiplying by square root of, well, maybe I only have a few points in there. So hopefully that's going to help us. And indeed it does. So let's write the recurrence. Okay. So for each of my triangles, okay, well, if they're completely below, I'm going to do a query in my second level structure. Also, if it's completely above, right, I'm doing a different query. In one case, I want to have the right endpoint above. In the second case, the right endpoint below. But for all of them, I do a query, which is going to take me this much time. And then for square root of r of my triangles, I have to do a recursive call on a two-level tree. Okay. And again, if you think about it in terms of the master theorem, since I have here square root of r and here, well, roughly n divided by r, you would expect that you roughly get square root of n. Here I also have square root of n, so in the end you don't get a blow up. And, well, I can pick this epsilon prime and my r in such a way that the whole thing again solves to n to the 1/2 plus epsilon. I guess you can imagine that if you are adding, so if I add a third level, okay, again, well, in the third level, I again plug in this, so nothing happens to the query time, so you can use as many levels as you like. Of course, you can imagine that in practice, since this constant is going to get bigger and bigger, in practice it's not going to be such a good idea to use a 10-level range tree or a 10-level partition tree. Right? But in theory, when n is really, really large, so asymptotically, this is what you get. Okay. How much storage? Maybe you can simply see this. Okay, so for each of these nodes in the first level tree, I have this second level tree. So at the root of the whole tree, I have a second level tree which also contains all the points, so that's O of n. All the children of the root, okay, every point goes to exactly one of the children. So all these associated structures together again contain n points. Okay, so at that level, if I look at all the trees together, it's again O of n. Yes, similar to what I did here, except now I don't have 2 children each having n over 2, but I have r children, but again the size sums up to n. So per level I have n. Well, the number of levels in a partition tree is log n. So I get n log n. Okay, and if you want, you can write the recurrence. Okay, where the crucial thing is that per level it sums up to n. That's here. If I look at all the children and the number of points in that child, that sums up to n. And that's the crucial thing to show that it's n log n. Okay. If I would have a partition tree with 3 levels, what would be the storage? N log squared n. Right? Because now here I put NW log NW, or in other words, if you sum it for a level, it will be n log n. And per level you get n log n, so you get n log squared. If you have a 4-level tree, n log cubed. Okay, so, well, this is the summary. For any epsilon, you can construct a data structure that uses n log n storage, such that you can count all the segments or report intersecting a query line in n to the 1/2 plus epsilon time. And, well, instead of a 2-level partition tree, you could also use a 2-level cutting tree. And now you simply get the bounds for 2-level cutting trees. So n squared storage and log squared n query time. Okay. Okay, so let's do this. So maybe a third, somewhat more complicated example is 2D ray shooting. So let's say I have the following problem. So I have a set of line segments in 2D, and I want to pre-process such that if I have a query ray, I can report the first line segment that I hit. Okay, and the query ray could start everywhere, be in any direction. So maybe first a simpler question. Suppose that all the segments are disjoint, and I know that all my rays are horizontal. How would you do it? You sort the endpoints. Yeah, so you can do something like, well, you can sort in Y and then do, but there's actually, and then, but if you do that, you would need, I don't know, maybe like a 2-level segment tree or something like that, but there's a much simpler solution. Like this one? Yes. Very good. So you can have a trapezoidal map, a horizontal decomposition. So through every endpoint, I draw a line to the left until I hit the next segment, and to the right. So actually, I forgot to draw this one. So you do that for all the endpoints. Now you get these trapezoids, and then if I do point location with the starting point of my ray, then if I know in which trapezoid I am, I also know which line segment I hit. Right? If it's to the right, it's the right boundary. If it's to the left, it will be left boundary. So trapezoidal map has linear complexity. You can do point location in log n time with linear space. So you get linear storage and log-n query time. So now what happens if the segments can intersect and maybe the query can be any direction? So if the query is still horizontal and the segments can intersect, well, then I could still use this solution, but the problem is that now in my trapezoidal map, I should also add something for the intersection points. So that would be, well, since there can be n squared intersection points, I would have n squared storage. And if the ray, if I don't know that the ray is horizontal, then, well, the whole thing breaks down because I don't know in which direction I have to do the trapezoidal map. So I want to do something else. Okay, so we're going to have a data structure with, well, almost linear storage, so n log to the power 3, and this much query time. So you can already see that this is probably going to be some kind of multi-level partition tree with 4 levels or something. Okay, so what is the high level view of the structure? So I want a structure that is going to do the following. So the query is this ray. So first I'm going to somehow select, in a number of canonical subsets, all the segments that intersect this line. Okay, and we just saw actually that you can do that with a 2-level partition tree. Okay, now I have all these canonical subsets of elements that intersect this line. Then I'm going to distinguish between 2 types of segments. The ones, like the green ones, where this point, the starting point, is actually below the line through the segment, and like this or this or this, where the starting point is above the line through that segment. Okay, so the answer could be in both of these cases, but I'm going to do it separately. Okay, so I'm going to have another. So I've selected all the ones that intersect this line. Okay, it's a number of canonical subsets. So if you look at such a canonical subset, I'm now going to select the ones where this point is below the line through that segment. Okay, again, point below a line, so that's another half-plane constraint. Okay, so I can do that. Once I'm now at a canonical subset of that level, okay, I'm left with segments that all intersect this line, and for each one of them, the starting point is below the line through that segment. Okay? So for each of those lines, think about the half plane which is below that line. Okay, so the half plane that we know contains this point. Take the intersection of all those half planes. So this one intersected by this, intersected by this, and intersected with this. Then I get this gray region here. Okay, that's the common intersection of all these half planes. Yeah, so in dual space this would be a convex hull, but here it's easier to think about it in here in this space, because what I want to do is I have this canonical subset. I'm going to build a data structure, and the data structure is going to be a data structure on this convex polygon. Well, it's an unbounded polygon, and it's a data structure such that if I want to do a query with a ray shooting query with a point inside this polygon, that I can answer this quickly. Okay, so, and then, like in this case, if this tells me that that the first edge of my polygon that I hit is this one, then, well, that edge of the polygon was generated by a segment, then this segment is one of the candidates. So can it happen that, okay, let me first go here. So it's going to look like this, my data structure. Level 1 tree, select all the segments with the left endpoint below the line through the ray. Level 2, select all the ones with the right endpoint above. Okay, so when I get here, I know that each of these segments will be intersected by my line. Level 3, select all segments where the start point of the ray is below the line through that segment. Right, so all these ones where it's below. Level 4, ray shooting in a convex polygon. A data structure for that. Okay, so my query, it would be something like, okay, search with this line in the first level, with this line in the second level, search with this starting point in the third level, and then with the ray in the fourth level. So if I do that, then I end up in lots of these level 4 structures, right? Because here I select a number of nodes. For each one of them, I go to the second level. I select node. For each one of them, I go here. I select. For each one of them, I go there. So I end up in lots of different polygons. So I get, some node that corresponds to something like this. And I answer a query, and maybe for another one, looks like this, and I get a segment and so on. So I'm going to lots of these level 4 structures. In each one of them, I do a query. Then I find lots of segments. And then I simply look at all of them. I take the one that is closest to the starting point. Okay? So, and that would be the answer. So one question would be, can it happen that we get something like this? So I have my this is my level 4, this is one of my polygons. So it's generated by some segments. Okay. could it be that when I do a query in this polygon, so my polygon is going to look, well, so here is my polygon. So can it be that I do a query, in the polygon I hit this edge, but the segment that generated this line is somewhere else. So I think that I hit this segment because I'm looking at this polygon and this edge corresponds to this segment. But actually this segment is not here but here. Can that happen? Well, if it happens, we have a problem. So I guess the answer is no, it cannot happen. Exactly. So if you look here, then by the time we get to this level 4, we only have segments that intersect the line through my query ray. So in a situation like this, where the query ray is going here, and it's not intersecting this guy, then this would not show up in my level 4 structure. Okay, so this shows that, well, this is, I get the correct answer. If you think about it, about the query time, so if I have a 3-level partition tree, right? 3-level partition tree, then I had the query time is n to the 1/2 plus epsilon, and the storage is n log squared n. So now, if I have a 4-level tree, okay, so instead of 3, I would get a 4-level partition tree. Well, we saw that the query time remains the same, and this becomes a 3. Okay, but now I have a 4-level tree, but the 4th level is not a partition tree, but a structure of array shooting in a polygon. So the question is, what happens? Well, ray shooting in a convex polygon is actually easy. You can do binary search with the direction of the ray on the convex polygon. And so if I have, for this structure here, okay, so I have a convex polygon, oops, and if I want to do ray shooting, I can essentially, you can always do binary search on the boundary. So if you think about it, you can get the storage is log n, is n, and the query time is log n. So that means that this structure here actually has better performance than if I would plug in a partition tree. But it also has linear storage, but it has only log n query time. So clearly, if I analyze the performance, then it's going to be better than something where all my levels are partition trees. So this bound with the log cubed here also holds, and with this storage bound.
So I think you missed it. Do you perform one query on the upper hull and then one query on the lower hull?
Yes, so here I'm selecting all the ones where the start point is below the line. For those, when you take this intersection, you get a polygon which is unbounded there, and then you do the query there. You also need to select all the ones where it's above, and there you get the opposite. There you would take the half spaces going up, and you get a polygon like this, and you do a query in those as well. But you need to do the selection because you need to know whether you have to look at the half plane going this or the other way. Okay, so this is what you get, and you can also use cutting trees. I guess the square here should probably be to the power 4. Okay, so, well, I guess the last part was going a little bit fast, so maybe the details are not completely clear, but what I hope is that at least you see that it should be possible to apply these techniques in this case. Right? By saying, okay, what do I have to do? Okay, I want to do ray shooting, so let me first select everybody intersecting the line. Then, if I already know that they intersect the line, let me select the ones that are, to a certain side of the line. Then, if I know that my starting point is to, let's say, below all these lines, then I just have to look at this convex polygon and so on. So, when you have to solve a query problem like this, the way to think about it is to start essentially decomposing the problem into saying, okay, I need, the one satisfying this condition and this condition and this condition, and then maybe I have something left where I need to do something else, like shooting in a polygon or something like that. And then for each of these conditions, you can, depending on what the condition is, you use a different structure. So if it's a half-plane condition, you would use a partition tree or maybe a cutting tree. It could also be that one condition is a half-plane condition in 2 dimensions, and maybe the second condition is something in 3 dimensions. Okay, then you have a partition tree in 2 dimensions where this association is going to be a 3-dimensional partition tree. Okay, also possible. So essentially, if you're used to this, it's just juggling with all these data structures a little bit, and then something comes out. Oh.
The time is timed, or think about it?
No, so for all these things, again, the bounds can be improved a little bit. So this should be, this should be n to the power 4, but actually you can improve it to log n. Here also this epsilon is not needed. Sometimes you can play some tricks to get this log cubed a little bit down, but So none of the bounds I'm writing are tight. All of them are sort of almost tight, right? So it's not possible to, if you want to have log or polylog query time, you cannot get n squared n root n or something. So n squared versus polylog. So those things are always tight. So at a high level it's tight. If you look at the details, n to the epsilon or log or something, then it's not tight. Okay, so here's a summary. As soon as you can express your query problem as, satisfy condition 1 and 2 and 3, and these conditions are half-plane conditions, then you can apply this machinery. Actually, also, if you want to have something where it's condition 1 or condition 2, so, you can think about that. You have to sometimes change things a little bit, but it's basically the same thing. So, for instance, these things you can all do. There's in this one, given a set of segments, the query is another segment, report all the ones intersecting that segment. Okay, what's the condition? Well, when does a segment intersect my query? Here. Okay, so when does this segment, for instance, intersect this query? Well, first of all, it should intersect the line through this query. So one endpoint should be below the line, the other endpoint should be above the line. Okay? But also, this segment should, this query segment should intersect this line. So this endpoint should be below this line, and this endpoint should be above that line, or vice versa. Right? So I get 4 conditions. Endpoint of data segment being below the line through the query, other endpoint being above that line. Condition 3, endpoint of query is below the line through that segment. Condition 4. Okay, so we can have a 4-level partition tree. Here, you have a set of triangles, and the query is a point, and you want to report all the triangles containing that point. Okay, what's the condition? Well, the query point should be above this edge, above that edge, and below that edge. Or actually above the line through this edge, the line through this edge. And so it's a 3-level partition tree. Okay, so this is a little bit more tricky. Anyone? I guess you have to have seen it to know how you can do this. So here the trick is that what you can do is you can take your points in the plane. You can map them to some points in 3-dimensional space by taking a paraboloid in 3-dimensional space, mapping them to the paraboloid, and then the query, the circle, you also map it, you get a circle on the paraboloid, and actually you can take a plane through that circle, and then you can say, well, finding all the points inside a circle in 2D, it's the same as finding all the points, let's say, below a plane in 3D. Okay, so you could use 3-dimensional partition trees to solve this 2-dimensional problem. Although actually, then what you would get, you get the bounds from 3-dimensional partition trees, meaning you don't get n to the 1/2 plus epsilon, but n to the 2/3, 1 minus 1 over d. And you can actually do it using more complicated techniques. You can also do it in square root of n in this case.
You cannot map 2 times in 1-dimensional space. I'm looking for the point in intervals.
No, because here, if I have a point which is here, it would be contained in the x range and in the y range. Yeah. Okay, so, and again, if I have something with t levels, then the storage would be n log to the power t minus 1, query time this, and here you also get bounds. So maybe to close, one more remark. What I said earlier was that sometimes you have maybe level 1 is, let's say, a 2-dimensional partition tree, and level 2 could be a 3-dimensional partition tree. Okay, so now the question is, what are the bounds? Because one is 2-dimensional, the other is 3-dimensional. So what do you think? Who thinks that you get the 3-dimensional bounds? Who thinks you get the two-dimensional bounds? Who has no idea? Okay. So you always get the bound from the highest dimension. Right? It's, for instance, if you think about, cutting trees. Oops. Cutting trees. Okay. Let's say the first level is three-dimensional, the second level is two-dimensional. Then even without the second level, you're already using n to the power 3 at the first level. N to the power 3 plus epsilon. So by having a second level, you're never going to use less storage. So definitely you're never going to get the two-dimensional bound. Okay, so the first level already has n to the power 3 if it's a 3-dimension. So that's something we need at least. But then we also know that a 3-dimensional tree with a 3-dimensional second level tree would simply have our bound n to the power 3 plus epsilon. So a 3-dimensional tree plus a 2-dimensional second level is only better because these second level trees use slightly less storage. So it's not going to get worse. So if you put together all these levels, you have to look at the worst level that you have, and that's going to determine your bounds. Okay, I guess that's more than enough for today. I hope you get some feeling of what is possible. Once basically this is something where you have to use it a few times, and then you will see that it's actually not very complicated, but the first time and the second time and maybe even the third time that you do it, it looks very complicated. But it's actually, it's when you apply it, it's usually, if you know how to do it, it's fairly standard, I could say. I mean, it's complicated standard technology, but it's fairly standard technology. I guess this is probably the last slide. Okay, are there any questions? An example where the first level is two-dimensional and the second level is three-dimensional. Okay, so one example could be, although here, is I have a set of points in the plane. Okay, so I have points. And so on. And I'm going to do range searching with a triangle. Okay? But I know that the triangle always has a vertical edge and a horizontal edge. And the other edge can be anything. So it could be this, or I don't know. It could be this or something like that. Okay? So you would say I have 3 edges, so I need 3 levels. Okay? If I look at this edge, well, because I know that this edge is horizontal, I actually have a one-dimensional partition tree, or just a binary tree if you want. Okay. To find then all the points that are to the right of this one, well, that's just the x-coordinate should be bigger than this x-coordinate. So the second level is also going to be a one-dimensional partition tree, which is just a binary search tree. Only for the third level, which can have any orientation, I need a two-dimensional partition tree. Yeah. Okay. Of course, here you can say, well, I just built a tree which can answer queries with any triangle, and then I can also answer queries with this triangle, and that's it. And since the query time is going to be determined by the worst level, also in this solution, the worst level is this third one, which is two-dimensional. You get the same bounds. Yeah. So if you look at, sometimes if you start looking at whether you have these epsilons or logs, then there might be a difference in those things. Right, and it's a bit. Essentially, you could say, okay, if at some point I have a level which is a half plane constraint in 2D, and the rest is in 3D, you can just say, okay, let me add, let's say, a dummy third coordinate and then pretend it's a three-dimensional constraint. So that's also possible. But it's a little bit, and you don't see that in the final bound, but it's a little bit overkill, you could say. Okay, I guess everybody is ready for a break now.